Hi, and welcome to this video that accompanies our paper. Satellite servicing and space debris removal are critical for our continued sustainable use of space. Ever since the first demonstrations of using a robotic manipulator to service an orbiting spacecraft were performed, research in this field has accelerated. The goal is to eventually send a chaser spacecraft into orbit that autonomously and safely docks with a target. This technology would also help prevent the runaway growth of the space debris population. In order to capture a target spacecraft using a robotic arm, two things have to occur. First, the chaser has to move its robotic arm to capture the target. Then, the chaser has to fire its thrusters to stop the combined system from spinning. If the target is spinning quickly, you can see this type of maneuver would be very complex. And there is plenty of research on both of these individual components. Recently, the Naval Postgraduate School released some research where they combined the capture and stabilization of the target into the same problem. In other words, they developed a technique where the chaser captures the target in such a way that the combined system has no angular velocity after capture. This means that, if done correctly, the chaser does not need to use extra fuel to despin the system after capture. And the folks at Naval Postgraduate School successfully did this. They developed a real-time optimization system which you can see captures the target in a way that the combined system does not spin after capture. Inspired by this previous work, we build upon it and apply machine learning techniques to the same problem. This allows us to develop advanced capture techniques while reducing the engineering effort involved and improving performance. The type of machine learning we use is called deep reinforcement learning. It trains a neural network, shown here, to accept the state of the system and calculate a guided acceleration signal. The chaser then has to track that guided acceleration signal in order to complete the task. We communicate the desired behavior to the neural network through a reward signal. The neural network then, through trial and error, repeatedly simulates a chaser trying to capture a target, tweaking its behavior each time in order to try and receive more rewards. If we select our reward function carefully, we can then encourage the desired behavior. We decided to give penalties when the chaser strays too far from the target, when its arm moves into a locked position, and we end the simulation early when the chaser collides with the target. We give rewards when the chaser captures the target properly, although we withhold rewards when it docks at a big angle or when it docks too aggressively with the target. We also give a penalty proportional to the combined angular momentum at the moment of capture to encourage capturing the target in a way such that the combined system is stabilized. These videos show the behavior learned as training progresses. Through trial and error, over millions of simulated capture attempts, the desired behavior is learned. Now that training and simulation is complete, we export the trained neural network for use in experiments at Carleton University's Spacecraft Proximity Operations Testbed. Here, we have two spacecraft platforms that float on a flat granite table using air bearings, creating a near friction-free environment. The positions of the platforms are tracked using a 10-camera phase space system mounted to the walls. The spacecraft platforms use thrusters to maneuver across the table. The platform shown on the left is the target with a docking port, and the platform shown on the right is the chaser with a 3-link robotic manipulator. The first experiment we perform has the target spinning at 10 degrees per second. The chaser takes the state of the whole system, passes this to the trained neural network, which returns a desired acceleration signal. The chaser's onboard controller then tries to track that acceleration signal in order to capture the target. As you can see, the chaser successfully captures the target, and it does so in a way such that the combined system has no post-capture angular velocity. This is the first, to the best of our knowledge, use of AI techniques to enable spacecraft capture in an experiment. The second experiment we performed had the chaser starting from a different initial condition and the target spinning in the opposite direction at 5 degrees per second. The same neural network is used here to guide the chaser to capture the target in this new scenario. Again, the chaser captures the target and stabilizes it. Next, the first experiment is repeated, but with perturbations applied to the chaser. Perturbations were not seen during the training, so this is an excellent test of the robustness of the learned guidance model. Since the neural network is calculating guidance signals in real time, it simply adapts to the current situation autonomously and captures the target regardless. Lastly, we tried perturbing the target, adjusting its attitude and bringing its angular rate to 0 midway through the experiment. Again, capture was successful. We should point out that all these behaviors were learned in simulation and transferred successfully to experiment. In addition, the neural network was trained only once, and that same network was able to perform all the simulated and experimental scenarios shown here. It encountered initial conditions and perturbations not seen during training. Lastly, all these behaviors were learned to maximize the simple reward function we designed. We did not handcraft any of the behavior. This is the first demonstration of AI techniques to perform spacecraft capture in an experiment, to the best of our knowledge. And it unlocked the ability to capture faster spinning targets than was possible in previous work. Thanks for watching. You can find all of the details in our paper, and all the code has been open sourced on GitHub. Feel free to contact me if you have any questions.